polynomial function. Now, what does a polynomial function look like in terms of a function of two variables? It's going to have things like this: x squared plus maybe y to the third plus x squared y to the fourth. This is considered to be a polynomial function in two variables. You're going to have x's and y's raised to different powers, and they can actually be multiplied times each other as well. That's a polynomial function. When we graph that, we should expect to see nice, smooth stuff, no craziness. Now, if you do a rational function, which is going to be a polynomial divided by another polynomial, then we should expect to see smoothness, except possibly where we have division by 0. There we would expect to probably see asymptotes, just like we saw with rational functions in Cal 1. And then if you take two continuous functions and you compose them together, then you're going to maintain continuity as well. Don't worry too much about this. It's just telling us that things behave well as long as our functions are these categories of functions: polynomials, rationals. We shouldn't expect any crazy behavior. And of course, we can't prove continuity, because to prove continuity, we need to prove a limit exists. To prove a limit exists is hard for us to do.
Prove continuity on that one we just
That one we just did, we could, yes. All right, that's it for 11.2. 11.3. Yeah, 11.3. Y'all doing all right? About 30 minutes? When I started that section, remember what I said. That's not like a mission critical type stuff. I mean, I'd like for you to do your homework, see if you can mess with those limits. But if you're totally missing the point on those and can't figure it out, you'll be okay the rest of the way. All right? Here we go. I'm gonna turn the light down a little bit so you can all go to sleep now. I just want to make sure you can see this next image real good. All right, partial derivatives. So finally, we're going to start talking about derivatives of these surfaces. So in Cal 1, right, we all are very comfortable with the main idea of the derivative in Cal 1, right? Give me a function in blue. The derivative represents the slope of the tangent line at some given point, right? So at every point on that curve, I can move around, and I will have tangent lines at every point, right? And each of those tangent lines will have its own slope, and the slope of that is dictated exactly by the derivative function, right? That, fine, right? No issues. Okay, but now, when we go into a function of more than one variable, like this one right here, look, this is the function, sine of x minus y plus cosine x. This is the graph of that surface right here. You know, it's kind of a cool looking surface, right? And if I go to some point on that surface, man, I'm having trouble with this thing. It's not behaving the way I want it to. All right, you get the idea. There's a point, right? If I go to that point and start talking about the slope of a tangent line, it doesn't make any sense anymore, because there are a bunch of points that would possibly be considered to be tangent at that point. There are a bunch of lines that you could consider to be tangent at that point. Do you all agree with that statement? Like, let me take the point to the top. Let me see if I can get it to move to the top of this. Let's say we're up here at the top, right? Then did you all agree that a line that would be like that would be, you could argue, is tangent, right? But I could just take that line, I could spin it around like that, and any of those lines would have worked, right? So there's not a unique line that would be tangent. So what we do is we construct this idea of a partial derivative, right? And it's a very simple yet beautiful and elegant idea. And what it does is it says, let's use what we learned in Cal 1. we learned that if you have a flat sheet of paper and you have a function, then we can find slopes of tangent lines. That all makes sense to us. So on this surface that I have here, let me move this point back where we can see it. This point here has an x and a y coordinate, right? Whatever it is, it has an x and a y. What I'd like to do is imagine that I take this y value and fix it, okay? Hold that y value as a constant. Do not let it move. And now I'm going to let you change what the x value is. Then if I do that, your y value, if you look at this graph, this is the x and that's the y. If I hold the y value constant and change x, I'm going to move along the curve, right? But I'm always going to be moving along a curve where my y stays the same the whole time, right? So let me show you what that looks like visually. I'm going to hold the y value constant, which does this. It basically cuts through the surface with a plane, right? And that plane represents where all these points are where my y value is staying the same. If I come in from the side, you can see that every point on that curve has the same y coordinate, right? So my y coordinate is fixed. If my y coordinate is fixed, and then I just rotate it like this, and I take the surface out, it makes perfect sense to talk about a tangent line, right? You're back in Cal 1 looking at it almost like two-dimensionally now. So we should be able to find the slope of that line, right? If we hold the y constant, treat x like the variable instead, just x, then we can move this around and we can find the slope at every point, can't we? Holding the y constant, letting the x move. But there's nothing that says that we had to do it that way, right? We could have instead gone back to that point and held the x to be constant and let the y change, right? If I do that, my plane is going to cut through this way. Let me rotate it. Let me show you both planes. This was holding y constant, right? That's y constant. Here's x constant. You can see that those two planes are orthogonal to one another. And we get those two different pictures. Do y'all see the two different pictures? Let me take the other one out where we fixed y. See, if we fix x to be constant and then turn and look at it from this side, now again we have a curve, a different curve, right? This curve is different than the one we just looked at that was in green. And so it makes perfect sense to talk about the tangent line there, and then we can let the y value move around and talk about the tangent line at each place, right? Making sense? Yes?
If you cross the tangent line from both points, would that give you a normal vector off of the slope?
Yeah, that's the next section. So what this is, well, we have to be careful because right now we're working with scalar functions, right? Scalar functions. So in order to define a plane, we need a normal vector off the plane. I think what you're saying is if we take these two tangents and cross them, we should get like a normal vector for a plane. That's exactly right. We just have to be careful because the slopes of these lines, the slopes of these tangent lines are not vectors yet for us, right? They're just going to be a number that's going to represent the slope. So there, yes, we are going to go there. We're going to go there for sure. In fact, that's exactly what I was going to show you next. If I take that surface back in here and I do both of those cuts, right? Hold the x, y constant. I get two tangent lines there, right? Two tangent lines. And let me take out the plane. There are my two tangent lines. Those two tangent lines uniquely define a plane that is tangent to that curve at that point, right? There's only one plane that goes through that point and contains those two lines. And so when we talk about functions of two variables, we will have tangent planes as opposed to tangent lines. And the next section, I think I have it open actually. The next section, this is, right here. The next section, this is 11.4. Hey, there we go, tangent planes. So that's exactly the next thing. So I can remember when I started to like put this thing together, right? When I was a student, I kind of didn't understand what a partial derivative was. Like I knew how to do it, but I wasn't quite sure visually what I was doing. So I hope that this helps you see that when you're fixing one of the variables, you're turning it into a Cal 1 problem. You're figuring that out. And then you let that variable go and fix the other one, and now you've changed your perspective and looked at the curve from the other direction, and you're finding that tangent line. All right? All right, this is just a bunch of definitions, but there is some notation we need to make sure we're clear with. So the key idea here is that to find a derivative at some point, we will need to either hold the x constant or the y. Okay? You can't hold them both constant at the same time. If you hold them both constant at the same time, then everything's a constant, and the derivative of a constant is going to be 0, because nothing is moving, nothing's in motion. So we have to hold one or the other, which is why we call these partial derivatives, because you're taking something that used to have two variables and you're holding one of them constant. So you're partially getting the derivative by holding something constant, as opposed to being able to handle the whole thing. So here's our notation. Given a function, z equals some function of x, y. If we hold the y constant, okay, if we hold the y to be constant, then we will call that the derivative, we will call that derivative the partial derivative with respect to x. When we say with respect to x, we mean the y is being held constant. And the way we denote it is we do not use this notation anymore. Remember this? This used to mean take the derivative back in Cal 1. We can't use that notation anymore because this does not tell me at all what I'm holding constant and what I'm allowing to move and change. So instead we write this f with this subscript x. This subscript x is almost like the prime used to be. This tells me I'm taking a derivative, and I'm letting x be the variable and letting the y be held constant. Yes?
Can we also do d dx?
Yeah, there's a couple of others. I have some more notations for you, all right? Was there another question? So this means take the derivative of that function, treat x like the variable, hold the y constant. Now if you want to do it the other way around, right, and you want to take the partial derivative with respect to y, that means you're going to hold the x constant, and this is the notation for that. And I have an example. So let's do this example. What you see up there is a polynomial function, right? That is a polynomial function because it contains x's and y's raised to various powers. I would like to know what the partial derivative of f is with respect to x. That's what this means. That means I'm going to hold the y constant, and I want to know what's happening at the point 2, 1. So there's a surface. I go to an x value of 2, a y value of 1. I go up to the surface, and I'm holding the y constant, slicing it, and looking at it from one angle. I'm trying to find that slope. So first thing first, I need to figure out what this derivative is. So I need this first. First, I need to take the partial with respect to x. To do that, I'm going to look at this right here, and everywhere I see a y, I'm going to act like it's a number, like a fixed number. So I'm just going to act like it's the number 1. Whatever number you want it to be, just in your mind, just think of it as a constant. So what is the derivative of y cubed if y is a constant? 0. 0, because y is a constant, right? Imagine just for the sake of argument here, that y is 2, right? Then 2 cubed would be 8, and the derivative of 8 would be 0, right? So I get 0 there, plus. All right, now I'm not treating, x is my variable, right? So what's the derivative of 2x back from Cal 1? 2. Okay, so that's 2. Okay, plus. All right, now we've got x squared times y to the 5th power. Normally you would be thinking product rule here, wouldn't you maybe? But y is a constant. So constants come for the ride, don't they? So I'm going to treat this y to the 5th like it's a constant, so I'm just going to write down y to the 5th. Okay, times, now all I'm going to focus my attention on is what the derivative of x squared is, which is 2x. And then finally, what's the derivative of 10? 0. So our answer here, let me clean it up a little bit, is 2x y to the 5th plus 2. That is the partial derivative of that function f with respect to x. Okay? Now, to figure out what's happening at the point 2, 1, all I do is I just evaluate that, replace x with 2, replace y with 1, 4, 6, I get 6. Yep. Questions on that? I want to go back to the picture real quick because I wanted to kind of like show again what we just did, but I want to ask a question. Where's my show surface? Okay, for this right here, we just held the y to be constant, right? So we did something like this, right? We held the y to be constant, so we sliced through, and we got this function. And I said it's like a Cal-1 problem, right? That's what I did say. My question to you is, if this is a Cal-1 problem, if it's a Cal-1 problem, why is my partial derivative with respect to x have 2 variables in it? Because if I'm in Cal-1, everything we did in Cal-1 had 1 variable in it. Why does my answer have 2 variables? Hold on, I want other people. Any idea? Hold on. Okay. What's being held constant? The y value is being held constant, right? So if y is being held constant, then really it looks like 2 variables, but it's not because the y is a constant. It's being held, right? And if y is being held, then this would be a linear function, wouldn't it? It would be linear. Now, we're not actually looking, that's not the actual graph of that surface, because doesn't that look almost like, well, it's not even quadratic. It looks kind of quadratic, but it's not. Okay, good. Let's move on to the next part of this. So I'm going to now find the partial with respect to y of this function. And I'm going to move it up so I can get in here and do this. The only difference between part A and part B is the thing that you're treating as a constant and the thing that you're treating as the variable. So first things first, I need the partial with respect to y of this function at xy. So I'm treating y like a variable, x like a constant. Right? X is the constant this time. So the derivative now of y cubed is no longer 0, it's now 3y squared. And then 2x, well, x is a constant, so that's going to be 2 times a number. That's still a number. Derivative of a number is going to be 0. And then plus, and then just like before, it looks like product rule, but the issue here is that x squared is going to be a constant. So that's just going to come for the ride. And then times the derivative of the y to the 5th, which is 5y to the 4th. And then finally, the derivative of 10 is 0. There we go. Who has a question on that? Anyone have a question on where I got that from? You good? And now just plug in 2, 1, and we're done. So I'm plugging in 2 for x and 1 for y. Guys, I don't want to make an example out of you. I don't want to. But all I hear is voices in that corner. And it's my responsibility to not let you be a distraction to the class. I've made this clear. The only reason I'm not kicking you out is because you do participate, you know? You answer questions, you're paying attention. But try and do it without the dialogue, all right? Please. All right. Or find a way to like communicate telepathically. All right? Do something like that. As long as I don't hear you whispering and your neighbors don't hear it. What do we get here? What is it? 23. Okay, there we go. So we cut it a different way. We go to that point, look at the slope. It's going to be pretty steep, right? Shit, right? So now the function's a little more complicated, right? Got chain. Got to bring the chain in. So the first part of this is asking for the partial of this function with respect to x. That means I'm going to treat y like a variable. Sorry, did I just say that? I didn't. I just said the exact wrong thing. This is what happens when I get distracted with other things. Okay? I'm going to take the partial of this function with respect to x, which means I'm treating y like a constant. X is the variable. When I look at this function, I have composition, sine of this, right? So I need the chain rule. The derivative of sine of something is cosine of it. So I put cosine inside of this. I do not touch it because all I'm doing right now is chain rule. That's the first part. Do y'all agree that derivative of sine of something is cosine of it? Okay. Times, now you can go inside and take the derivative of the inside. And that is quotient rule. You have to do derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. All that stuff from Cal 1, right? So I'm going to get it set up here because it's going to be a pretty big mess. Yeah, I'll do it like that. Right? So let me take the derivative of the top first. I'm doing quotient rule. Derivative of the top, x is my variable, y is a constant. X is my variable, y is a constant. Who wants it? What's the derivative of the top? Who wants it? What do you got? Y. Why? Why am I asking?
X to the first power. So
Yeah, I got you. I'm messing with you. So y, good, times the bottom minus, all right, who wants the derivative of the bottom? Go ahead.
2x. Oh, wait.
Doing derivative of the bottom. Go ahead. It's with respect to x, so we're treating x like the variable, y like a constant.
So 2x.
2x, that's it. Right? Because when you take derivative of x squared, you get 2x plus the derivative of y squared. Well, y is a constant, right? So derivative constant is 0. So that's just going to be 2x. That's derivative of the bottom times the top. The top is xy. And then all divided by the bottom squared. Is that not the quotient rule? Okay, that's the quotient rule with this idea of a partial derivative and holding certain things constant. Who has a question? Does anyone have a question on where any of that came from? Everyone understands what's happening? All right, let's do the next one. The next one is to do this partial, but this time with respect to y. Not a lot's going to change, is it? Other than I lost the function there. Let me see if I can squeeze this in right here. So now y is my variable, x is my constant, right? Same game. I still have to do composition, cosine of xy over x squared plus y squared times, and then again quotient rule. Who wants the derivative of the top for me? We're holding what constant? X. So who wants to give me? Someone new. You're not new. Hold on. Wait. I want to give some other people opportunity. Anyone else? Go ahead, Georgia. I want the derivative of the top with respect to y. Just x. Good. And then I'll continue with the bottom, multiplied by the bottom, then minus. Okay, who's giving me the derivative of the bottom with respect to y? You gave me that. Go ahead. Sorry. Get you next one. To what? 2y. Doesn't it look a whole lot like the other one? Mm-hmm. And then x squared plus y squared squared. Hey, hold on a second. Are these the same answers? They look kind of the same, don't they? Like that's the same, right? These don't look exactly the same though, right? X, Y. But maybe if we distribute everything out, maybe they are the same answer. I wonder. Are they? I don't know. I'm wondering.
It may not be the same answer just because inherently they're two different planes.
Well, I think this is an open question. Is it always the case? Is it sometimes the case, right? What do you think? Do you think sometimes they are the same? Do you think they're never the same?
Well, no, because by the definition you gave us of a partial derivative,
Uh-huh.
one's basically fixed on one axis, one's fixed along the other axis, to where they have to be orthogonal.
Yes, I'm saying if you look at these algebraically, we know that in this one they're different because here y is a constant, here x is a constant. So I agree, they're different in the sense of that. But in terms of just looking at it algebraically, purely algebraically, x's are x's, y's are y's, are they the same, is what I'm getting at. Let's leave that as an open question, all right? Because we're going to answer it in just a moment. Well, maybe not today. There are different notations for partial derivatives. Just like in Cal 1, there was different notation for derivatives, right? You had the primes, then you had the dy dx, right? You had that for derivatives in Cal 1. We have all these, the following are equivalent, TFAE, all right? The following are equivalent. So that's the notation we started with today. This means you're gonna treat x like a variable, y like a constant. Another way you could write that is just f with the little subscript x. And then everyone will know you want the partial derivative with respect to x. Or you can write this. Now we're saying here that we're given a surface z equals f of x. So if you write this, be careful, it is not d, I'm not writing df dx, right? That's a derivative from Cal 1. This is a partial derivative, so we no longer use this. We use this notation here, df dx. This is actually called del, yes? Is that what you're going to ask me? So del f, del x. But I will mostly say in this class, the partial of f with respect to x, that's the way I'll say that. And it's understood that symbol there tells you it's a partial. It tells you you're going to treat here x like the variable. You're going to look at that function f, and you're going to treat x like the variable. And that means anything that's not x, like the y, is a constant. Another notation is this one. Partial of z with respect to x. This is saying, again, you're looking at this equation, which is a function of two variables, x and y, and you're going to differentiate treating x like the variable, and it is implied then that y is the constant. Then you have this notation, which means we're going to take the partial derivative, we're going to treat x like the variable, and then this is what we're taking the partial derivative of, f of x, y. So this says we're about to do this operation of taking a partial derivative, treating x like our variable, and that's what we're taking derivative of. And then I like these at the end. That's a weird notation, huh? F1, F subscript 1. Let me explain what this means. You know, in this notation right here, it said, hey, take derivative of f, treating the x like your variable, right? This is saying, take the derivative of f, treating your first variable as the variable. See, what's our first variable? X, right? So this would mean we're going to differentiate with respect to x. If this was a 2, then it would be differentiate with respect to y, because that is the second variable. It would not mean a second derivative. It would just mean differentiate with respect to the second variable. This is the same concept, except we put a capital D in front that says, you know, take the derivative, right? Treat this first variable as your variable, and that's the function you're differentiating. This is the same notation, but instead of using the ones, we use the x. I mean, look, I don't make this up, all right? So these are all the different notations you may or may not see in the rest of your mathematical life, all right? Okay, so where are we? We've defined what a partial derivative is. We've done a few examples, right? Define what a partial derivative is. Done a couple examples. We have new notation, right? And so in Cal 1, what we did is we learned what the derivative was. We did some examples, and we looked at different notations. And then we said, hey, guess what? You can do not only the first derivative, you can do the second derivative, and third derivative, and fourth derivative, right? So now we have higher order partial derivatives. Was there a question?
I was just going to say the order of the last one, it was F1 with respect
yeah, if I said, hey, do this, that means you're taking derivative of that with respect to y. Yes. But that's different than the higher order derivatives, which go like this. This is the last thing we'll talk about today. If you're given a function of x and y, then if I want you to take the derivative twice, I need to tell you what I'm treating like a variable, what I'm treating like a constant. So look at this notation right here. If I want you to first treat x like a variable and y like a constant, figure out that derivative, and then do it again, treating x like the variable again, that's the notation. I will write fxx, or f11, or partial with respect to x of partial of f with respect to x, or this, or this. These are all in your notes, all right? The ones you need to focus on are these. Those are the ones. Look at this one. You do the partial with respect to y first, and then you do the partial with respect to y again, you write y. Please pay attention to the next one. If you do the partial with respect to x first, then you do the partial with respect to y, you write fxy. So the way you read this is you're doing derivatives from left to right. So I do that partial with respect to x first, then the partial with respect to y. If I want it the other way around, I'll do the partial with respect to y first, then the partial with respect to x. As you might suspect, this extends into third, if you want third partial derivatives, fourth partial derivatives, fifth, right? So I have 1 minute. Let me see. Do we want this? Let's set this problem up. We won't do it, but let's set it up. Oh, remind me, there's a bonus question I have for you. But you'll have to stay a little bit after class to hear it. Okay, so I want to find all the second partial derivatives of this. Let's just talk about what they are first. The first second partial I could find, or the first one is fxx, right? That would be taking the derivative twice with respect to x both times. I could also do fyy. I could also do fxy, and I could also do fyx. Those are the only four possibilities when it comes to second partial derivatives. I can either do x twice, y twice, x first then y, or y first then x. So this is where I'll pick up class next time, but if you want to get ahead or look at it, think about what this problem would be. First thing you do is you take the partial of this with respect to x. You get an answer. And then whatever that answer is, you just do it again, right? Or here you do it with respect to y, and then you take that answer and do it with respect to y again. Here you switch. You do partial with respect to x first, and then whatever that answer is, you treat it the other way, right? You do it with respect to y next. All right. So this bonus question, I think the way I'm going to do this is I'll only give bonus to the first